Alright, so today we're going to be taking a look at the laws of thermodynamics. Basically, there are four laws of thermodynamics. Laws number 1, 2, and 3 were created in that order. The Zeroth Law, as they call it, or law number 0, as I've written there, was actually created at a later point, basically as a logical constraint, which is basically common sense, but it had to be written down because otherwise you would have that horrible feeling of incompleteness. So let's take a look at the laws of thermodynamics. Starting with the zeroth law, the most important should be common sense. If two systems are at thermal equilibrium with a third, then they are at thermal equilibrium with each other. Basically, if they have the same temperature as a third system, then they have the same temperature as each other. Basically, if we were to draw this, so basically we have systems A, B, we'll have a third system C. And basically what we're saying, if both systems A and B are at thermal equilibrium with C, thermal equilibrium meaning that there's no heat transfer between them, so Q dot AC equals 0, Q dot BC equals 0, that means that they're not transferring heat between these two systems. If both A and B are at thermal equilibrium with C, then that means that A and B are also at thermal equilibrium with each other. So Q dot AB must also be equal to 0. It is important to note that the thermal equilibrium we're discussing here is for natural heat conduction between the two systems. So they are physically contacting one another. There's no conductive heat moving between them. Effectively, this defines that if the temperature is the same, then there's going to be no heat transfer between those systems. Now, the first law of thermodynamics has to deal with internal energy, which basically states that the internal energy of a given system follows the law of conservation of energy when energy is being passed into or out of the system. Now, this is generally expressed as the internal energy of the system, or the change of internal energy of the system, delta U, is equal to the change in the heat of the system. So for example, if you have heat being added, let me just separate these. If you have heat being added, so delta Q net, that's net heat being added into the system, minus the work being taken out of the system, delta work net. That's the work being removed from the system. So essentially, the increase in the internal energy of a system is related to the net heat being passed into the system minus the net work being removed from the system. I can actually draw this a little bit better with a quick little sketch here. Here we have our system. We can have heat being added in, Q net in, and we have some property U of the system. Basically, U is going to be equal to the initial state, and then we're going to have some Q net in. If we have the system do some work for us, we're going to be taking work out. That's going to be minus work out. Essentially, basically all it's stating is that energy in a system is conserved. It's not created out of nowhere, and it's not removed into nothingness. Energy is conserved, so the internal energy change of the system is related to the heat that we put in and the work that we take out, such that it follows the law of conservation of energy. Interestingly enough, if this was to have mass input as well, some mass input, we're going to have plus, we'll call it U prime. Basically what that is the that's the internal energy per unit mass of the system, and that's going to be times the mass added. This is all just purely hypothetical to illustrate the point. Basically, conservation of energy is still being conserved when we're adding mass to the system, simply that we also have to consider the amount of internal energy being added per unit mass of the system that we are increasing. So yeah, the first law of thermodynamics, the internal energy change of a system follows the law of conservation of energy. Energy is not created, energy is not destroyed, it is simply transferred from one form to another. You can add heat energy, add thermal energy, you can have the system do work, you can add mass to the system, but the internal energy change of the system is proportional to that. It does not change outside of that realm. Finally, we get to the second law of thermodynamics, which has to deal with entropy. Basically, the total entropy for interacting systems always increases. And let's draw this down here. Basically, for entropy, it is a measure of what you could call chaos of a system. So say, for example, we have the letters A, B, and C. And we want to make a system out of A, B, and C, but we can order this in any way. So it could be B, A, C, it could be C, B, A, any number of those. You have about 6 options of that. Essentially, what entropy would be is a measure of the possible states that could enter. So for example, the formula for entropy would be S equals the Stefan-Boltzmann constant times the natural logarithm of the number of states that can be associated with this system. So for this ABC system here, there's 6 possible states, so it would be the Boltzmann constant times the natural logarithm of 6. So basically, if we have 2 systems here, we'll call them A and B, and these 2 systems are interacting with each other in some way, then the total entropy of this system is always going to be increasing or equal. So if we were to plot entropy on a chart here between A and B, we'll have, and I don't know, some value of time. No matter what we're doing, this total entropy of the overall system has to be always increasing. It's never going to go down. And this is true for any interacting system. So if we had an open system, for example, system A, and it's exhausting into the environment, well, then we have to consider the environment as being part of our system, and we would see that the rule of the second law of thermodynamics does hold in that case, as the total entropy of the system being considered would indeed increase. And finally, we have the third law of thermodynamics, which doesn't actually end up being used as much in classical mechanics or in day-to-day life, which basically states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. So basically, let's say we have a bunch of helium molecules sitting in this space. If we were to then cool this down to absolute zero, then since these are helium atoms and there would be basically one microstate, there would be a single microstate that they would form into at absolute zero, then theoretically the entropy would be equal to Stefan-Boltzmann constant times the natural logarithm of the number of microstates. In this case, it would be 1, which is going to be equal to 0. Now, not all systems are going to be equal to 0. There are some systems in which you'll have some residual entropy that might be, I don't know, 0.01 or 0.57 or whatever. Basically, for those systems, they still approach a constant value at absolute zero, simply that constant value need not be 0. Now, just to talk a little bit further about entropy, there's a few ways in which entropy is actually generated between 2 interacting systems. Number 1, we can have heat transfer over a finite temperature difference. Number 2, we could have some friction, such as, for example, a fluid boundary layer against the wall of a pipe of some kind. We could have unconstrained expansion. So, for example, popping a balloon would generate a lot of entropy, as basically there would just be chaotic motion as it expands freely. So you could call it free expansion as well. And finally, you could have a mixing of two substances. Now, when you're studying thermodynamics, there's a few important formulas that you end up using over and over. One of them is for internal energy. So that would be that formula that we saw above. The change in internal energy of a system is related to the law of conservation of energy, the change in heat of the system minus the work done by the system. So remember that this is basically the engineering notation. This is heat in minus heat out, and this is work out minus work in. So this will be Q in minus Q out. And this is work out minus work in. We basically use that notation through engineering and some other professions basically because what we're interested in is we're interested in knowing what the work out is. Now if we consider a system that we have here, let's call this just some system. This system is going to have pressure P, volume V, etc. Basically, if we want to calculate the work done by the system, then we have to consider how this system is interacting with its environment. So basically, if we define work, work is defined as an integral of a force over a distance. So if we take a look at this system, if we have a force that's going to be on the walls of the system, so we'll say that F is equivalent to pressure times the area of the surface, or we'll call it A. So our force is the pressure over the area of that surface. If that surface moves at all, then we have this ds, basically the change of the boundary location. So basically our work is going to be equal to the integral of pressure times area times ds, the change of that boundary. But interestingly here, this A times ds is actually the change in volume of the system, because area multiplied by the distance over which the boundary is moving gives us a volume. So if we were to take example of a cube, if we have an area over this surface, and this surface moves by some delta x, then what we have is a change in volume. The volume would be x, y, z. The volume would be changing to x plus delta x, y, z, and thus we would have work done by the system based on that delta x. So effectively, what we have is work being equal to the integral of the pressure in the system multiplied by the differential change in volume of the system across that pressure. So if the volume changes, there will be work done either by or to the system depending on the direction that the volume is changing. If we were to take this in differential form, then the differential work is equal to the pressure times the differential change in volume. So we can then plug this back into our internal energy equation, or energy conservation, now that we know what our work is defined as. Our change in internal energy is related to the change in heat of the system minus the pressure times the change in volume of the system. Now another important thing to note would be the heat supplied to the system, and basically this delta Q, this heat added, is proportional to the change in temperature of the system. Basically the temperature of the system is just the average kinetic energy per molecule. So if we have thermal energy being supplied, that's being converted, or change in average kinetic energy for the particles of that system, thus creating heat. Basically the whole derivation of how to actually calculate the heat input is defined partially by the Boltzmann Boltzmann constant, which kind of helps to bridge the micro to macro level changes in energy. However, it's not really that simple. There's a heat capacity depending on the number of degree of freedom of molecules and quantum level states. Basically, what it all boils down to is the heat into the system, delta Q, that's the heat added to the system, or the net heat into the system, is related to the heat capacity of the system times the change in temperature that we observe. Now, what we're going to be defining this as is a constant volume heat capacity. That would basically apply to if it was a solid, if it was a liquid, if it was a gas. We're assuming in this case that the volume of the system remains constant under a heat input. So therefore, we can write the change in internal energy of the system is equal to the heat capacity CV times delta T minus the pressure times delta V, and this is referred to as the boundary work, and this is the heat in the system, or the heat supplied to or from the system. Now, another important property to define for a thermodynamic system is what's called enthalpy, where enthalpy is simply defined as H equals U plus PV, where H is enthalpy, obviously, U is the internal energy, and this PV is basically a term for work. Essentially relates to the amount of work done by the boundary layer of the system to get to this specific, or to get to the state that it's in. So we'll call it boundary work. And some interesting properties about enthalpy here, since we already know what our change in internal energy is. If we were to write this in differential form, we'll say dH, the differential change in enthalpy, is equal to the differential change in internal energy plus the differential change in the product of pressure times volume. From calculus, we know that this is going to be equal to, based on the multiplication law of differentiation, we'll have P dV plus V dP. We already know what du is, so we can rewrite this by plugging in our previous equation up here. dH equals CV delta T, or since it's in differential form, we'll use dt, and that's going to be subtract P dV, pressure times differential volume, and then we have the rest of this equation, which is plus P dV plus V dP. And interestingly enough, these two cancel out, and what this leaves us with is the differential change in enthalpy is equal to the heat capacity times the differential change in temperature plus the specific volume times the differential change in pressure. Now this is all specific since I'm using these lowercase terms here, but you could also do this for the actual enthalpy, the mass product. So basically what we would do is we need to get this into a form that we can work with. If we consider an ideal gas, PV equals RT, so therefore this volume term, specific volume, is equal to RT over P. Or alternatively, we could also consider the differential pressure term, where we would have P equals RT over V. What we can actually get for our enthalpy here, since we know this is going to be differential pressure change, we can set that to R times the differential temperature change over the specific volume, and we get that the differential change in enthalpy is equal to CV dt plus, we're going to have V times R over V dt. These V's drop out. We get that differential enthalpy is equal to the constant volume heat capacity times the differential temperature change plus the gas constant, times our differential temperature change. CV plus R is our constant pressure heat capacity. So therefore, our differential enthalpy change can be written as Cp dt. That's our constant pressure heat capacity times the change in temperature. So when you're doing any kind of design work or engineering work or anything of that sort, two of the big equations that you'll need to know are going to be your internal energy being related to Cv dt and your enthalpy being related to Cp dt, and that is for a perfect gas. Now I want to look at entropy as well here, whereby we can define a process that does not change entropy. And that would be a process that is reversible, meaning that it can be undone after the action has been performed on the system, and it would also have to be adiabatic, which essentially means that there is no heat transfer to the surroundings, and thus no heat transfer over a potentially finite temperature difference. So there's what's called a Clausius definition for entropy. Delta S, change in entropy, is equal to the change in reversible heat over the temperature of the surroundings, and that would be, you also have plus the change in entropy that is irreversible. Now in a future video I'm going to be using this equation to define isentropic relationships for perfect gases. That will be in another video. Basically it'll define how two gases are related to one another through isentropic relationships, which is commonly used in fluid mechanics, especially in compressible flows. So I'm Arlington Matrix, and we'll see you in the next video.